Welcome to Sheridan College's online training of industrial electronic devices. This video is week 7, Introduction to IC Logic Gates. This session in particular is part 2 on truth tables and logic gates. Electric circuits can be as simple as a flashlight that uses a single series circuit, or as complex as a computer that uses thousands of circuits working together. In order to bring a systematic order to these circuits, electricians and engineers have developed a simple system to track the flow of signals, their condition, and the results of those signals. As an electrician, understanding the circuits and their functions is a core skill. When you move these skills to electronics, the same terms take on slightly different connotations. This lesson will introduce you to some of these terms. After completing this lesson, you should be able to explain an AND gate, complete an AND truth table, identify an AND logic gate, and explain, complete, and identify the same properties for OR, NOT, NAND, NOR, or XOR conditions or logic. Let's go over some key terms that we're going to be using throughout this presentation. The first one is logic. It's defined as a process of signal evaluation based on the flow of electrical signals to decision devices called gates, and the progress resulting in the outputs by the satisfactory condition of inputs to achieve a particular result. Okay, what that basically means is, in automation and electronics, we want a particular outcome to be achieved. By monitoring various inputs, we confirm that the process is working correctly and as expected. The flow of signals to the decision-making devices and the associated wiring and arrangement of these inputs, outputs, and controls is grouped together and called logic. You may have heard the term digital logic. Digital logic is a logic that works on a single digit change to resolve a simple true-false proposition. If the conditions are true, desired, then the signal may pass. If the conditions are false, the signal does not pass. Another term is logic gate. A logic gate is an electronic integrated circuit that evaluates signals applied to its input terminals and will execute an output signal based on the design intent of the gate and its internal circuitry. It is a two-state device that is a conditional gate for passing a signal. That is to say, if the conditions are true, then the signal is passed on. Another key term is binary. Binary is any system that consists of two things or numbers. It is a counting system using base 2, 0 and 1. In electrical terms, binary is a system where a signal that is off in the de-energized state, it is represented by a 0, and the on or energized state is represented as a 1. Let's begin by looking at a simple circuit and the current or signal flow. The circuit shown is a series circuit. In order for the light to work, both the switches must be closed. In this example, any other combination of the switches will not work. If you were to describe how this circuit works, you would name the switches and then say, when switch A is closed and switch B is closed, then the light, or output, will turn on. This is the foundation of electrical and digital logic. It is simply the following of a signal from its source, in this case the battery, through any conditional devices, in this case our switches, to the final desired output, in this case our light. This particular circuit arrangement has a name in logic. It is called the AND condition, or AND logic. With this condition, there is only one desirable solution, but more than one possibility. This circuit gives us 4 possible outcomes depending on the state or position of the switches, but only one correct solution. When A is off and B is off, the light is off. When A is on and B is off, the light is still off. When A is off and B is on, the light still remains off. When A is on and B is on, then the light is finally on. Now would be a really good time to go over some common terms that are used. All of these terms are interchangeable and often happens within the same sentence. When we're talking about electrical circuitry, we're dealing with the presence or absence of voltage or current. So we would call that normally off or on. But these take on slightly different meanings depending on whether you're looking at logic in the paper form or whether you're looking at an actual tester. So we have synonyms that are applied across the board. So the word off can also be heard as false, low, open, de-energized, or be expressed with the binary value of 0. On can be expressed as true, high, closed, energized, or the binary value of 1. It's important to keep these in perspective, and when you start with one, it would be important to use the same term at the same time. In other words, if you want to use the word false for off, then use true for on. It will avoid some confusion. Let's apply some of these synonyms to the same circuit that we've just examined. So, when A is false and B is false, the light is false. When A is high and B is low, then the light is low. When A equals 0 and B equals 1, the light equals 0. When A is closed and B is closed, then the light is closed or energized. Now that we have seen the results of an AND condition, we could create something we call a truth table. A truth table is a visual reference that shows the output result for a given set of input conditions. The truth table shown here is for our AND table, and it represents our simple series circuit. It is read from left to right, and the outcome is always on the right-hand column. For example, we see that we have one section for A, one section for B, and another section for light. Normally on a truth table, they will only have zeros and ones. This makes it simpler to read. But again, if we follow it through, it is working out the same logic we just reviewed. So when A is 0 or off, and B is 0 or off, then the light is 0 or off. Since we have substituted letters to represent our inputs, let's finish our table by substituting the letter for the outcome of the conditions involved. In this case, we'll use the letter C. Notice that each of the lines still corresponds to the same logical conditions of the inputs that satisfies the output. We have seen how we can take an entire circuit and reduce it down to its simplest form by creating a truth table. In electronics, a large amount of circuits are contained into a very tiny space. We've already seen in our previous lessons how a diode can replace a switch, and the resulting reduction in size because diodes are much smaller than physical switches. Similarly, when drawing an electrical or electronic logic circuit, many of the lines and switches used that current flows through are simplified into a single symbol. After all, the resulting output of two or more conditions is more important than the physical device or devices that are actually used. We call these electronic equivalent devices and their symbols logic gates. Just like our first example for the AND condition and our AND gate, each gate has a truth table and an associated internal logic flow. In order to clearly understand the inner workings of our logic gates, we will be showing you the equivalent electrical circuit only in a slightly different format called relay logic. Relay logic is a process of recording and tracing electrical controls and power flow through drawings constructed of symbols representing the physical devices such as relay coils and auxiliary contact switches, lights, etc., but whereby all the devices are shown in their shelf state, that is the way you'd find it if you opened the box brand new, and drawn in a ladder-like layout with rungs of logic. They're read from left to right, top to bottom. Current coming from the left, flowing through the devices, and returning on the right-hand column. Although it's beyond the scope of this course, we will use relay logic examples to help visualize the logic conditions. Relay logic and its cousin, ladder logic, which is used exclusively for programmable logic controllers, are read again from top to bottom, left to right. Let's start with one that we've already seen. Here are three representations of our original series circuit, the AND condition. The top example is drawn in relay logic. The devices are identified by their symbols, two switches, a coil, or a light. The middle example shows a circuit used by a PLC, a programmable logic controller. The symbols are simplified because the PLC only checks for two inputs being high to energize the output. It doesn't know what the real-world devices are. The bottom line shows an electronic version of this circuit. Notice it has been simplified even more, and that the two inputs are no longer in series, but appear to be in parallel. This is because the shape of the symbol tells you what circuit is embedded or contained within the chip. These single shapes or symbols represent the logic, not the components or the physical arrangement. If we were to look inside, we would find two transistors in series, with the emitter of one connected to the collector of the other, and two separate base connections. Again, in order for the output C to be on, both base A and B must be on. Another advantage of our transistor package is, whereas our light switch example came from a single source, our transistor can be monitoring two completely different sources. A might be checking for a manual switch, and B might be looking for a jog push button. Now let's begin to look at some of the other electrical conditions or circuits we can have. We're going to look at the OR condition. Our original series circuits required that both inputs be on to energize the output, A and B turned on C, which made sense electrically since the current only had a single series path to get to the light. Here we see a parallel circuit. This circuit offers more possible solutions to turning on the light. A parallel circuit offers more possibilities to activate the output, and the key word here is OR. With two inputs, the parallel circuit condition has four possibilities, but now there are three solutions. When A is low and B is low, the light is low. When A is high and B is low, the light is high. When A is low and B is high, the light is high. And finally, when A is high and B is high, the light is high. This is the truth table for our OR condition, and consequently the corresponding OR gate. As before, here are the equivalent circuits for an OR gate. Again, we have the two inputs in parallel. Either one of them or both will turn on our output. The bottom line shows the logic gate symbol for the OR gate. Notice its shape is different than the AND gate. Have you ever had an argument with someone who insisted on disagreeing with everything you say? Usually just to drive you crazy. And then, when you point out they're just being contradictory, they reply, no, they're not. Well, welcome to the land of naught. The not condition is actually not a function of the input, but rather a contrarian output condition. Let's closely look at the first example of our relay logic. With no energy applied to the coil marked ENGI, it would remain off. However, power would still flow through the NIV's normally closed contacts, energizing our output C. Normally closed contacts refer to the fact that when you first open the box, their natural position is to be closed. There's been no energy or change of state. So in this case, with the power off, those contacts would be closed, allowing the current to flow through. Normally, a low signal in becomes a low signal out. But in this case, the opposite has happened. In other words, the signal has been inverted. Now let's watch what happens when we have a change in one of our inputs. When A or B is closed, power can now flow to the INV relay's coil, changing its state. When this happens, the INV's normally closed contacts will open, shutting off power to the output C. Again, this is the opposite of what we would normally expect. Here, a high signal in became a low signal out. This function is called inverting the signal, and the bottom logic gate symbol shown is called an inverter. The truth table for the NOT gate or inverter shows the output will always be the opposite of the input. This is the function of the inverter. While not normally used on its own, it does form a part of other circuits. What would happen if we took an inverter and stuck it in line with the output of an AND gate, and then watched the new output? What would the truth table look like? Well, when you put an inverter in front of an AND gate, it becomes a not AND gate, or simply a NAND gate. And here is its truth table. When we look at it, we can see that it's the AND gate inverted. So when A is off and B is off, C becomes on. When A is on and B is off, C is still on. When A is off and B is on, C still remains on. But if A and B are both on, then we turn C off. The NAND gate behaves exactly as shown on the truth table. Whatever the original output should have been, the built-in inverter inverts it. A small circle on the output replaces the inverted triangle on the NAND gate symbol. Okay, let's see if you've been following along and can deduce something. We have a logic gate symbol here. From this symbol, can you deduce what its function is? Well, it's an OR gate with a dot, which means it must have a built-in NOT gate. So it is a NOT OR gate, or simply a NOR gate. According to the NOR, or NOT OR gate truth table, the gate's output will only be high when both A and B are low. Any other condition and the NOR gate will go low. Just to be clear, let's look at the truth table closely. When A is high and B is low, then the normally high output is inverted and the final output is low. Imagine you go to a fancy lunch restaurant and are told when you order, you can either have a salad or a soup, but not both, and if you're not going to have that, you can have nothing at all and leave. Well, this is an example of our last logic gate, the exclusively OR gate. The exclusively OR gate examines both inputs, but will only pass an output if one, but not the other, or not both, of the inputs is high. examining the XOR gate truth table, we find that it does not distinguish between the inputs, only that they must not be high at the same time. In other words, it's only checking to see for an inequality, not equality. Because A and B are low, then the output's off. A and B are high, then the output's off. It's only when there's a difference between the two that it acknowledges and will turn on an output. The XOR gate symbol has an extra chevron line in the input side to identify it from an OR gate. Although not very common, there is an exclusively NOR gate. As the name suggests, it takes the normal output of the exclusive OR and inverts it. The result is that it's looking for equality between the two inputs where both are either high or low. Please do not adjust your set. There is nothing wrong with this picture. These are examples of 3-input IC gates. The 3-input NOR gate and the 3-input AND gate are shown. The addition of an extra input doubles the number of possible outcomes. Here is our truth table for our 3-input AND gate. Notice how it is expanded. However, regardless of all the possible combinations, the result has not changed. A, B, and C inputs must be high to make D high. This is a 4-input OR gate. There are other 4-input devices available, such as a 4-input NAND gate or a 4-input NOR gate. We will show you the reduced truth table for this device. There's actually 2 to the 5th power number of solutions, or 32, and we'll end our exploration of the variations of the original 2-input gates. With a quick look at this truth table, you will see that any input will satisfy and turn on output Y. IC logical gates represent simple logical circuits and are the building blocks of larger, more complex electronic circuits. Each has their own truth table, which demonstrates the required inputs to set the final output. In our next video, we will be taking a look at Boolean algebra.